Okay. Wow. All right. So let me share my screen. Okay. Back to definition of vector fields. Just a quick recap. Last time we did what the definition of a vector field is, and keep in mind it's a function. It's a function that eats a point and spits out a vector. So for every point, there's a corresponding little arrow that goes with it. Cool. So the 2D vectors fields look like that, the notation, and the 3D vector fields look like that. And it turns out you've already studied a vector field in your past. That's right. Gradients are a very special vector field. So we looked at some pictures of vector fields, which is kind of cool. And we sketched a vector field, which was fun. So we're going to sketch a couple more vector fields, and then we'll talk about a very special kind of vector field. So check out this vector field, fxy equals 2xy. I could graph, you know, a whole bunch of points, like 50 points and 50 vectors, but I'm kind of lazy. I'd like to graph less vectors, but still get the flavor, establish some sort of flavor that somebody could look at and go, yeah, I get how that vector field is flowing. Because the previous one you saw, we didn't have to graph very many vectors here. And we saw that the flow looked like a wheel or a circulating jacuzzi or something. All right. So the step one that I need you to get, and if I don't see this on your paper, then prepare to lose a lot of points, is you set your vector field's magnitude equal to a constant. And this is called level curves and scalar fields. So you're like, okay, square root of, and then the sum of the squares of the components, set it equal to a constant. And then square both sides, and then take a look at that equation, and it turns out this is c squared. These are ellipses. So, what kind of ellipses? Well, if we wanted to get this in a standard notation or standard format for the equation of an ellipse, what I'm going to do is I'm going to let c equal 1, because that'll be one of my level curves. So then I'll have 4x squared plus y squared is equal to 1. And then the standard equation of ellipse, let me just remind you, looks something like x centered at the origin anyway, x squared over a squared plus y squared over b squared equals 1. And we don't have that look right now. But if I rewrite the first term and I claim that multiplying by 4 is the same as dividing by 1/4, then I'll have the standard equation of the ellipse. Why? Because this denominator is my a squared, and when you take the square root of that denominator, plus or minus a half are going to be the x-intercepts of the ellipse centered at the origin. And then this y squared term has a denominator of 1, so plus or minus the square root of 1 will be the y-intercepts. And then the ellipse is right there, very cute. And that's one of the level curves that we're going to graph a few vectors for this vector field. Okay, so then I'd like to see a chart. If I don't see a chart, you're not going to get credit, because usually the my math lab will just give you, they don't make you make charts and I'll do all this stuff by hand, of course, because, you know, it's online. So they'll just give you some pictures, multiple choice of different vector field graphs, and then you're supposed to just pick one. And just to avoid the lucky guesses getting the right answer, I want to see the work. So you graph some points here, and I'm just going to pick 4 easy points off of that ellipse. Easy points meaning the ones that are on the coordinate axes, because, you know, they're not too hard to grab off of there. And so on the left-hand side of the chart, you've got the points, and for each point, you have a corresponding vector. So these 4 points are when c is 1. And the vector is the 2xy. So twice the x coordinate, 2 times a half, will give me the first component of the vector, and then y is 0. So what does that mean? The 1, 0 is the vector that's a horizontal vector pointing to the right with its tip at the 1, 0. And so if you graph that here at the point 1/2, 0, it's going to be pointing like that. So that's the first guy right there. And then 0, 1, the corresponding vector will be 0, 1. And that is a vector that's pointing straight up. And if you move that vector so it's corresponding to the point, you'll have that. And the next point over here on the ellipse, -1/2, 0, has corresponding vector -1, 0, and that's pointing to the left, magnitude of 1. And then finally, the bottom point on that ellipse has coordinates twice the x, which is 0, and then the y, 0, -1. That's pointing straight down. Now, you could easily deduce that all of the other vectors that if you did pick other points off of this ellipse, they would all be pointing away from the ellipse with the same magnitude as everybody else. That's why they call it level curves in scalar fields. They share the same magnitude. All these magnitudes are 1. Is this enough vectors for the graph? No, I don't have enough vectors to give me the real flavor of this yet. So pick one more constant for your equation here. Suppose I let c equal 2 instead of c equal 1. So if I pick c equal 2, I'll have 4x squared plus y squared equals 4. And then if I divide both sides by 4, I'll get x squared plus y squared over 4 equals 1. And this is the standard equation for an ellipse centered at the origin. And so here, this guy's x-intercepts are plus or minus 1, and the y-intercepts plus or minus the square root of 4, so that's 2. So this ellipse, a little bit larger here, we'll pick 4 points, easy points, off of that ellipse, put them into our table. And so this one will have 1, 0, 0, 2, -1, 0, and 0, -2 for the points off that ellipse. And then the corresponding vectors would be these 2, 0, 0, 2, -2, 0. Notice that all of these vectors are also going to be pointing outward away, but their magnitudes are 2s. Okay, so all the vectors that are associated with this level curve are going to be larger. Oh yeah, got to make them big, magnitude of 2. And you can, deduce that, more vectors sticking out of that guy will also be pointing away from the ellipse with magnitude 2. And I'm done with that vector field. It's a nice graph. That's enough vectors that gives me the idea of how this vector field is looking. Okay. So let's do a super easy vector field that doesn't even require much. This is a constant vector. So I don't even need to do all the hard work for this one. What do you mean? Any point that I choose in the XY plane will have this constant vector 0, -1/2, which is just a downward facing vector that has a magnitude of 1/2. So it doesn't matter. I can pick just a bunch of points and, oh, those are too large. I need 1/2. It's got to be tiny. So if I just graph enough vectors sort of all over the place to indicate that this downward 1/2 magnitude, and that's enough. Okay, it kind of looks like rain. Yeah, kind of looks like rain. Now, the last example is a 3D vector field, and I'm not going to really ask that you graph 3D vector fields, and neither is my math lab. But this one's kind of interesting in that it's got a quick and dirty look to it, in that the first 2 components are 0. So the only component you worry about in 3D here is the z component. Okay, so what does that mean? Well, if you plugged in, say, x and y that are 0, so x and y are, your point is 0. Let's just say the point is 0, 0, 0. The corresponding vector would be 0, 0, 16. So here you've got this pointing straight up vector 0, 0, 16. But then any other point that you plug in here in the XY plane or wherever anyways, they're going to be less because, and you have to limit yourself to a domain there, disk of radius 4. The further away you get from the origin, the smaller the vectors. So you get closer, they get taller. So you kind of have to honor that. And so this is, and if you take in any physics, like if you squeeze a tube of toothpaste, if you imagine this opening to be the opening of your toothpaste tube, the velocity of the toothpaste molecules that are in the center of the tube move faster as you squeeze your toothpaste than the molecules of toothpaste that are closer to the rim. Yeah. So we can even talk about velocity of toothpaste. Toothpaste is a fluid. All right, I'm done graphing vector fields. All right, that's enough of graphing. Let's get to some more interesting topics that have to do with vector fields in this section. Conservative vector fields. What the heck? What does that mean? It has nothing to do with being conservative politically. Okay, so let's not go there. But I want you to notice in example B, the vectors all appear to be blank to the level curves from which they emanate. So this was the one we just did with the ellipses. Do you notice that this graph has a different flavor than the other graph? These vectors here look like they're all tangent to their level curves. Okay, that's interesting. You get that whooshing wheel. But these vectors here in letter B, do you notice that all the vectors are orthogonal to the level curves? And that's the blank word that we're missing there that we'll fill in. Orthogonal or normal. We could say normal. Normal. Okay. Now, because this is a property of gradients, and if you recall from gradients, yeah, that's right. A couple chapters ago, remember gradients are always normal to the level curves? Yeah. And we use that to our advantage, especially when we were dealing with surfaces and the 3D gradients were normal to the surface, and we were able to use those for the normal vector to the tangent planes. So that's key. That's very key. So because this is a property of gradients, it's normal to ask, could this vector field that had that nice graph where all the vectors were normal to the level curves, could this be somebody's gradient? Could it? And the answer is yes, it could. In fact, it is. Yeah, well, who cares? You care. Because here's why. This fact, some vector fields can be represented by the gradients of differentiable functions. Not all. Okay, don't get all excited. Not all. The ones that can are called conservative vector fields. So let's do the official definition of a conservative vector field, and then we'll get to the theorem that will help us figure out if a vector field is conservative or not without having to graph it. I mean, you could graph every single one and, oh yeah, this one's got vectors that are normal level curves. I guess this one's conservative vector field, and oh, this one, they're tangents, so not conservative. That takes too long. As you noticed, it's very tedious to graph a vector field. I hope you got that. Yeah, it is. So you want to have a quicker way of deciding. So here's the official definition of a conservative vector field. A vector field is called conservative if there exists a differentiable function little f, and this is known as a scalar function. It's not a vector field function, such that the vector field is equal to the gradient of f. Now, this scalar function f has a special name. We call that the potential function for the vector field, big F. All right, the potential function. So if I ask you on a quiz or exam, hey, go find the potential function for this conservative vector field, you'll know what I'm asking for. Okay. I hope you got to know some of your vocabulary. Yeah. Otherwise, you're going to be like Googling up, well, what the heck is a potential function? I don't know. Now, the word conservative, just so you know, is taken from the world of physics. It comes from classic physical law regarding conservation of energy. That's where the conserve is, conservative. So just a quick mini physics lesson, very fast, okay? The kinetic energy, that's energy due to moving around, plus potential energy, that's energy that's sort of storage energy. I'll give you an example of potential energy. Here in my bookcase, the books that are on the top shelf have more potential energy than the books on the bottom shelf. How come? Well, because if they fall on my head, they potentially have a lot of chance, the ones on the top shelf have a lot of chance of hurting my head pretty bad, especially these big wonkin' ones, okay? That's called potential energy, the potential to, to hurt. So by position of being at the top shelf, they're got a higher potential energy than the ones on the bottom. That sum is equal to a constant. And so that's an important physical law. If you take physics, you'll get more into that. And if you take thermodynamics, you'll get more into it also. Fun times. All right, here's the big theorem. We got to fill in the blank here. That's why you got to be in lecture. So how do you check to see if a vector field is conservative or not without having to graph the darn thing? Because that takes too long. Here's the quick test. And this is the 2D theorem only. I'm not going to give you the 3D yet. So don't ask me. All right. It's coming next week. So for a two-dimensional vector field, how do you check to see if it's conservative or not? So first, let's look at the notation for a two-dimensional vector field. And I use capital M and capital N for the components of the vector field. Your textbook uses like P and Q, and it's terrible. M and N is the more traditional. So you've got, and they're functions themselves. They're scalar functions of two variables. It's conservative if and only if the partial derivative of n with respect to x is exactly the same as the partial derivative of m as in Mary, with respect to y. And if you can show this is true, boom, you have a conservative vector field on your hands. That's right, people. That's all you need to do. Easy peasy. No graphs required. Now, once you figure out that, yes, you have a conservative vector field, because this equation is true, dn dx equals dm dy, it doesn't tell you how to get your potential function, little f, this scalar function. And so I'm going to show you the Rasky way to do it. If you don't listen to me and you decide when you're doing your My Math Lab to hit the view an example button 1, 2, 3 times, and you do it the way the book does, I'm just going to tell you right now, I'm going to take away your points. That's right. Well, you're not very open-minded. That's right. Not when it comes to this, because I'm showing you actually a shortcut, the easier way to do it. And if you're just going to ignore me and ignore my teaching and my direction, that's on you. You got choices, you know, and choices have consequences. So although a lot of times I am open to different perspectives and views, especially in my computer science class, boy, you should have seen yesterday's quiz. I had a couple people that got this one problem right. It was pretty hard. And they had two completely different approaches. And it was great. And I gave both of them full credit. Awesome sauce. But here I'm not going to be open to that. Okay, so you'll do it my way or the highway. But first you got to show it's conservative, because if it's not a conservative vector field, then no potential function exists. And I like to call this potential function mama. So mama is only going to be in existence if the vector field is conservative. Then we'll go get mama. Okay, here's a nice vector field. Conservative, yes or no? If yes, go get mama. Go get that potential function, little f. And what when you are finding the potential function, what you're claiming is that the vector field is the same as the gradient of your mama function. That's the definition. Here's the vector field. This is m and this is n. Okay? So dn dx, the partial derivative of xy with respect to x, is equal to what? Anybody want to tell me?
2xy.
I'm doing n first. dn dx is what? What's the derivative of xy with respect to x?
Y.
Yes, thank you. Okay. Now let's do dm dy. So what's the partial of x squared y, but with respect to y?
2xy. X squared.
With respect to y, you're holding x constant.
Yeah.
X squared.
Sorry.
Are these equal, yes or no?
No.
No! So this is not a conservative vector field. It's a vector field. It's a lovely vector field. And we can talk about it. And we could even graph it if they wanted us to, but I don't feel like it. But it isn't conservative. It isn't conservative, okay? So you're not gonna go find mama. You're not gonna go get a potential function because none exists. Although I have seen students, even though they get a no here, they don't listen to me like, oh, I'm gonna go off and get the scalar function. I'm like, what are you doing? There is no, well, I'll show you something and they'll do some work and I'll go, that's interesting. Thanks for the tip. Okay, here's another vector field. Letter B. Let's get D. Here's N and here's N. Let's do it backwards now. Let's get dm dy first. Okay. What is the derivative of 2x with respect to y?
0.
0. Yeah. Okay. What is dn dx? So here's n. It's equal to y. What's the derivative of y with respect to x?
0.
0. Thank you. Are these equal?
Yeah.
Yep. What does that mean? It's a conservative vector field. Woohoo! What does that mean? Go get mama. Go get mama. That's right. Go get mama. That means that there is a potential function. That's mama. It's a scalar function where if you did find the gradient of mama, it would be exactly this vector field. That's all. Now I'm going to show you the Rasky way to do this. The Rasky way to get the potential function. Again, I'm going to repeat this at the risk of being redundant because I know sometimes students need to hear things 5 times before they get it. I don't make that up. They actually did studies. Students need to hear things 5 times before it sinks in, which is kind of a lot. And that means I'm going to have to do this lecture 5 times in a row. So we'll be here till midnight. No, I'm just kidding. Okay. Just kidding. I'm going to give you this easiest way to find the potential function. You're first going to take the integral of m, the first component, with respect to x, and you'll get something. Then you'll take the integral of n, but with respect to y, and then you'll basically add the results, sort of. So I'll put a little double quotes here. You're sort of adding the results, but we're not really, truly adding them, as you will find out. Okay, so we'll talk about that when it comes, because this problem isn't going to bring that particular issue, but the next problem will. So first of all, what is the integral of 2x with respect to x? That's pretty easy. That's just x squared. Now normally you go plus a constant, but what I want to see is you're going to put plus a constant, but it might even be more than just a constant with just like a pure number. Because we integrated with respect to x, we're treating y as a constant also. So you basically acknowledge that. And if you don't, I'm going to take away a point every time you don't on your paper. You're going to put like plus g of y, plus some extra junk that might involve constants, which right now would be y's, things that had y in it, because y is considered a constant when you're integrating with respect to x. That's right. So now let's do the integral of n, which is a y, with respect to y. Well, that's pretty easy because that's just y squared over 2. And again, you want to acknowledge that you're integrating with respect to y now, not x, and you'll go f of x. So there could be some constants there, not just a constant pure number, but a constants plus x's. So I need you to put these little guys here, and every time you don't, I take away a point from your problem. So potentially, if it's a 10-point problem and you didn't put g of y and you didn't put f of x, that's -2 right there. I'm telling you right now how I'm going to grade. So just put those in there, even though they don't show up in the final answer. You'll see in a moment. So now your potential function fxy, and I do want you to write that down, equals, and now you add these together, x squared plus y squared over 2. And I say add, it's okay to add these two together because none of them are duplicates. We'll see in the next problem, if you get duplicates, you don't add the duplicates together. Be careful. Plus, and now since we've recovered the potential function completely, the only constant that we would get would be a pure number. And we're done. This is the final answer. This is the potential function for this vector field. Now, how would you check your answer? Quick and dirty way to check your answer would be go get the gradient of this function, of this potential function, and you better get the vector field, because this vector field is the same as del f, the gradient of the potential function. And we're done. Any questions on this?
When you said don't add the if something shows up twice, do you mean like if the integrals are like x squared and x squared, don't
No,
combine them at the end?
that will never happen, but let's wait till the next problem and then it'll become clear. Just be
Okay.
patient. Be patient. I'm getting there. This problem was an easy peasy problem just to so you kind of see the flavor of how the strategy is. Next problem, we're going to end up with some duplicates. You'll see. Okay. All right, so I'm done with letter B. Let's do letter C. All right, here we go. Here's a vector field. Cute. Is it conservative? Yes or no? Well, here's M and here's N. What is dm dy? So what's the partial derivative of 2xy, but with respect to y? I think it's 2x. Okay, what is dn dx? The partial derivative of x squared minus y with respect to x. I think it's 2x. Hey, they're equal. Yeah, conservative vector field. What does that mean? Go get mama. What do you mean go get mama? Go get the potential function. So you're going to go the integral of m with respect to x first. And so you're going to go, what is the integral of 2xy, but with respect to x? Not too hard. You're holding y constant and you're integrating with respect to x. So this looks like it'll be x squared y. And then acknowledge there's a constant which could involve y. You're going to go like plus g of y. Extra junk. And then you're going to integrate the n, but with respect to y. So you're going to integrate the difference of x squared and y here, x squared minus y, dy. Not too hard. You'll get x squared y minus y squared over 2 plus the constant extra junk that could involve x's since you didn't integrate with respect to x's. You got to acknowledge that for me, f of x. Okay, and I'm going to draw a line here. You're sort of kind of adding these together. So write down fxy, otherwise I'll dock you a point for missing notation. Yeah, I want you to write it. Equals, then what? So Hannah, check this out. Do you notice that x squared y is showing up in both of the integral results?
Yeah.
Those are called duplicates, or that's what I call duplicates. Like, hey, that guy's getting duplicated. Should I just add them together? No. Do not add them together. I don't want to see, well, x squared y plus x squared y is 2x squared y. Yeah, that's the ticket. I'm going to take away all of your points. Well, that's not very nice. Yeah, it is, because you didn't listen. What you're going to do is you're going to go, oh, those guys are getting duplicated. Just take one instance of it. One instance only. Take one of them. Don't add them together. Then we've got another term that isn't getting duplicated. So we're just going to put him in there, minus y squared over 2. And then we're done getting everything, but then acknowledge that we could have a pure number be the constant. Put a plus c, and voila, there's mama. There's your potential function. And that one involved the duplicates. Pretty cool, huh?
Sure.
Hey. Now, normally I would have put you in breakout rooms so you could go do the next problem together, but no time. We were jammed for time today. I apologize. So today I'm just going to be yapping up a storm. You know, what can I say? Yappity, yappity, yappity. Yeah, you know. So this one's tricky. I want to give you a full disclosure of where I get some of my inspiration when I create my exams for this portion of Calc 3, differential equations. What does differential equations have to do with vector fields? Well, for those of you who've taken DiffEq, you may remember solving something called an exact equation. And to prove it's exact, you have to actually check to see if dn dx equals dm dy. So quick survey. Has anybody taken differential equations yet? That'd be Math 253. And in the chat box, tell me, yes, you have actually encountered an exact equation. Yes or no? Anybody? Nobody's taken differential equations yet? No. Hell no. Okay, I get it. I've seen them in linear algebra. Oh, okay, interesting. Aaron, you're taking it right now. Okay, so did you do exact equations yet, Aaron, where you solved some diffie qs that were called exact?
We're doing it next week.
Oh, okay.
Yeah.
That's interesting. You're doing it kind of late in the game.
Mm-hmm.
I usually cover those early in the semester when I teach differential equations because they're first order. But anyway, I digress. So if any of you are going to be taking it, you'll be pleased to know that I taught you the quick and dirty way to recover mama. So Aaron, I'm talking to you. When your teacher shows you how to recover the answer to your diffie q, use my way. Except your final answer will look like fxy equals the constant. So instead of putting a plus here, you'll just put equals. Okay, I'm giving you a quick tip.
All right.
You're welcome.
Thank you.
If you have any issues with diffie q, come visit me in office hours. I'll be happy to help you. I love that course. Okay, so let's move on and let's go. Here's the m and then here's the n. What is dm dy equal to? What is the partial of negative 2y cubed sine 2x with respect to y? Well, we're really only differentiating the y cubed and then keeping everything else as a constant multiple. So you basically have the negative 2 times the sine 2x multiplied with the derivative of y cubed, which is 3y squared. And then when you clean this up a little bit, move the 3 over, you'll get negative 6y squared times sine of 2x. Okay, there's the partial of m with respect to y. How about dn dx? What is that equal to? Oh my goodness. Well, if you distribute the 3y squared, just so you kind of see what's going on here, and then you differentiate with respect to x, the 3y squared looks like a constant. So the derivative of 3y squared with respect to x is 0, plus 3y squared times the derivative of cos, which is a negative sign. We're using the chain rule, 2x times 2. But then when you move this 2 and this negative out in front and make it look pretty, you also get negative 6y squared sine of 2x. And these are equal. So yes, it's a conservative vector field. Yay. What does that mean? Go get mama. Go get mama. So, well, you know, you're going to go recover the potential function. So you're going to go, all right, I'm going to have to integrate the m with respect to x. So what is the integral of negative 2y cubed sine 2x, but with respect to x? Well, the negative 2y cubed is just a constant, right? And then you multiply that by the integral of sine of 2x. And I believe that's going to be a negative a half cos 2x, and then plus extra junk, g of y. And then clean this mess up. Let's reduce a little bit, and a negative times a negative is a positive. Okay, fine. So I'm going to get y cubed times the cosine 2x plus some extra junk. All right, now you're going to integrate the n with respect to y. So I have this 3y squared plus 3y squared cos 2x, and I want to integrate that sum with respect to y. So the first term is easy because, you know, the integral of 3y squared with respect to y, okay, that's not hard, y cubed, plus, and then this other term, the cos is just a constant multiple, so you'll have y cubed cos 2x, and then acknowledge the constant, and acknowledging that x is a constant when you're integrating with respect to y, so say f of x. Okay, do you guys see any duplicates here?
Yes.
Yeah.
I see duplicates right there. Should I add them together, yes or no?
No.
Do not add them together. I'm just going to get so mad at you. I'm just going to, Well, what do? Do you just throw it out? No, you don't throw it out. You just take one instance of it. Just take one of them. Okay. And I do have another term there. And now you acknowledge that you recovered everything. So the only constant would be a pure number. And there's your potential function. And we're done with that. So to recap, there's a very special kind of vector field out there in the world. It's called the conservative vector field, but not all vector fields are conservative. So to check to see if you have a conservative vector field on your hands or not, you do the quick test, the test for 2D. Does the partial of m with respect to y match the partial of n with respect to x? If yes, it's conservative, and that means a potential function exists. And it means if you did graph it, all of the vectors are orthogonal to the level curves. Cool. So let's look at a quick and dirty proof of why does this even work? Why does this test for conservative vector fields work? You know, when we check to see if dm dy is equal to dn dx or not, how come that even works? Like, what the heck? Well, remember your gradients? Recall that if you were given, you know, a function and somebody says, go get the gradient of f, and this is good for you to know, the gradient was what? It was a vector that contained the partials of the function. Okay, yeah, so what? Well, this is key for you to know here. Okay, so suppose there exists a potential function f such that your vector field is exactly equal to this gradient. So this fx here is the same as m, essentially, your m of xy, and your other component here, the partial with respect to y, is your n. So I'm going to fill in these blanks here. Okay. So then what? Well, when you take the derivative of m with respect to y, or if I use the subscript notation my, what are you doing? You're taking your fx and you're differentiating him with respect to y. Okay? And then similarly, when you're saying, okay, what is dn dx equal to? Well, you're taking the fy and you're differentiating it with respect to x. And that gives you dn dx or nx. Okay, these are the same. Okay, now what are we saying? Well, by the equivalence of mixed partials, remember fxy is the same as fyx. You can conclude that dm dy, or if you want to use this notation my, is the same as dn dx when you have a gradient on your hands. And that's why any conservative vector field that you're looking at is really somebody's gradient. That's how you can conclude it. That's a little mini proof for you. And if you just understood this proof, that means you're able to, for me, you're proving to me, you're demonstrating that you can make these really nice connections in your mind about what's going on. So it's not like, oh yeah, conservative vector field, I just use the theorem. I don't know what I'm doing, but you know, the teacher said to go do it. It works, whatever. You know, true understanding comes from getting what I just did here rather than superficial knowledge. Okay, now let's do a definition here as well as some more vocabulary. So if you've got a differentiable scalar function on either, you know, R2 or R3, the vector field that is formed by getting the gradient, that's called a gradient field. And we already know that the function is called a potential function. Those level curves that I did for you when I did some of the graphs, those level curves, of the potential function are called equipotential curves. So that's where the potential function is constant. And we did this back in chapter 15 when we studied regular level curves. Okay. So let's do some, a little bit of fun and play with this idea of equipotential and curves and stuff like that. And this is similar to what you're going to see in your MyLab math homework. So I pulled out basically a problem similar to what's in the MyLab math homework and threw it right here. So here you go. We're going to find the gradient vector field f. It's basically just go get the gradient for this potential function. And then we're going to plot the gradient field together with the contour map of f. And this is just level curves of f. That's a fancy schmancy way of saying go get the level curves. So we're going to sketch some of these equipotential curves and then explain how the gradient field vectors are related. Okay. And you're going to see the same kind of thing happen here. You're going to see we get those vectors are normal. to those level curves. It's going to happen. So here we go. So we're going to get what's called flow curves. All right, flow curves, everywhere orthogonal to the equipotential curves. Okay, so chapter 15 material. When is x squared minus y equal to a constant? This is how you get level curves. This is a good review for the final. Why? Because the final is coming up in 4 weeks. Yeah, it's coming up in a month, people. Get ready. So what does this remind you of? Well, I claim if you rearrange it, these are parabolas. Yeah. You know, you can let c equal 0. If you let c equal 0, you get y equals x squared. That's going to be one of the level curves. Okay, right there. And if you let c equal 1, you get y equals, you know, x squared minus 1. That's another parabola. And so you're just going to get a family of parabolas here. Okay. So there you go. So here's when c equals 0. This is when c equals -1. This is when c equals 1. And just a whole collection. And these are called equipotential curves. Okay. And if you graph the vector field and using, so what's the vector field? So the vector field is equal to the gradient field. They're one and the same. Well, what do you mean? Well, the well, excuse me, let me just use the notation. Big F with a vector on the top of them, xy, is the same as del little f xy, which is just this vector. Go get the partials. Okay, so what do I mean? Well, your vector field is going to be, well, what's the partial of f here with respect to x? I think the partial will be 2x, and then the partial with respect to y will be -1. This is the vector field. If you go graph this guy, and again, you can make a chart, and you can, I'm going to pick points off of the equipotential. You could pick one of those parabolas, you know, pick a point, 0, 0, 1, 1, 0, 0, 1, 1, -1, 1. You know, these are points. And then you put the vector here. And you would have corresponding vectors like this. And you do that whole thing. And so it's going to end up where, at least for this one level curve, because I'm too lazy to do all of them, you'll get these vectors like this, this. Okay, like that. So it's going to turn out that this vector field is looking like it's orthogonal to these equipotential curves. And what I like to do, because shoot, man, I don't like graphing vector fields. It's such a pain in the rear end. I like going to my wonderful graphing situation here and graph it that way, because you know, why do this? So here I go, okay, 2x, and then my y component for my vector field is negative, oops, not y, it's this -1. And then when I graph it, you can kind of see, let me spruce this up a little bit. Okay, so check out this vector field. It's kind of hard to see, but you can see sort of the flow of it. As you get out here, the vectors get larger and larger as you get further away from the origin. So there's a nice look. If I go a little bit in, zoom in, to keep doing that, boy, this is going to be a fun day. One of these fun days. Oh, man. Okay. So that's a picture of the vector field. You can see all the tips of the vectors kind of look like dots because this software doesn't do so well, but they're mostly kind of flowing downward. It looks like a downward flow, down and out, kind of not quite like rain, but kind of like that. So that's kind of a cool looking vector field. Interesting. But the key that I want you to get, if you're not getting it, is that the gradient field, that's the gradient, is orthogonal. This is the key, that the takeaway, orthogonal to the level curves of the potential function. And there you go. Okay, so that's the key takeaway. You take that away, you're good. So why are gradient fields so important? Well, in physics, they talk about it a lot. So if you take a physics course, you'll get, they're useful because they kind of give you access to that physical meaning of the gradient. So let's say your function, your mama function represents a temperature in a conducting material, then the gradient field evaluated at a point indicates the direction that the temperature is going to increase most rapidly. You've heard that before. It's where the gradient points you. Steepest ascent, temperature increasing most rapidly. And if you go in the opposite direction of your gradient, the temperature decreases most rapidly. So things are starting to cool off. And in general, when you have a hot conducting material like a hot coffee cup or whatever, you know, things cool off until they reach equilibrium. So heat flows down the gradient from hot regions to colder regions. So if you ever hear flowing down the gradient in your physics class, now you know what that means. And water on a smooth surface tends to flow down the elevation gradient because, you know, gravity. Okay, so let's find a gradient vector field for a given potential function. And now at your Briggs, they like to use phi instead of little f for their mama function. So don't get freaked out when you see this phi and start thinking, oh, are we doing spherical coordinates? No, they're just using the Greek letter phi in a different context. Okay, it's like, oh man, that again? Oh dear. So they're giving you the scalar function. That's the potential function. That's mama. That's your mama. And if you were to go get the gradient for mama, you would get the vector field. Okay, so here's a picture of the level curves of phi. And how would you get these level curves? Well, you'd set mama equal to a constant. And it's like, well, yeah, okay. And if you graph this, and you could take tangent of both sides and get actually lines that are have the origin as an intercept. That's where you get all these lines. That's the level curves for the potential function. And if you graphed the vector field that's the same as the gradient, now the hard part is how do you take the derivative? And this is what I wanted to do. So let's, before we take the gradient, let me remind you, because some of you may forgot. Do you guys remember how to take the derivative of arctan of u? Using the chain rule, it's u prime over 1 plus u squared. Does anybody recall this from Calc 2?
Yes.
Yes.
All right, fantastic. Well, so if your u is y over x, and you're taking fx, you're differentiating with respect to x, you're going to go, okay, 1 plus the u getting squared, ugh. And then the derivative of y over x, if I rewrite that as yx to the -1 and then take the derivative of that with respect to x, you'll get y times -1 times x to the -2. That looks, if I clean it up, which is not that clean, I'll get that. But then what? Well, this x squared can swing down, that's legal. And then if I rewrite this by distributing, it doesn't look too bad. It looks like -y over x squared plus y squared. Okay. When I get fy using the arctan derivative formula, I'm going to get, well, the derivative of the u, y over x, with respect to y is just 1 over x. If I try cleaning this up, it's not going to look as good because it'll still be a complex fraction. What do you mean? After I distribute here, one of the x's cancels, but the other one doesn't. So I'm going to multiply by a special version of 1, x over x. So it looks a little prettier, that's all. And then distribute. And then I'll get x over x squared plus y squared. So the gradient, which is basically our vector field, which contains these partials as components, looks like this. And if you graphed this vector field, you would get the picture, well, some of the vectors anyway, the picture that they're showing to you right there. Looks like a wheel rotating around. But notice that those vectors are normal, making 90-degree angles with the level curves. Aha, and that's the key. That's the takeaway from that diagram. Orthogonal to level curves.
I do have a question on one part.
What's that?
when you were doing your derivative part
Sure.
of the f of x,
Yeah.
why is it one? Why is for the why is it negative y over x squared? But then it's just y over x on the bottom.
Not y over x, it's just 1 over x.
For the f of x.
Okay, because I think I know your question. Do you see this u prime right here, Nathaniel?
Oh yeah.
I was doing the u prime. So when I
Oh,
was taking fx, my u was the y over x. And when you differentiate y over x with respect to x, and I just rewrote that as yx to the -1, that's what I was doing right here.
okay.
The y is a constant multiple, and the derivative of x to the -1 power is -1 times x to the -2, which if you rewrite it, oh, I'm very sorry, is -y over x squared. Yes?
Yeah, okay,
So my
yeah.
u prime is, I'm putting the u prime right there in the numerator because that's what the chain rule tells me to go do. Does that help?
Yeah, that does. That's the thing I was confused by.
Okay. Any other questions? Everybody good? Okay. All right. So now let's look at a couple of memes here. I saw this about a year or two ago. This is supposed to be a high school physics teacher talking to his high school student. Mr. Fox, is there a reason why you're standing on your chair? It's to boost my energy. I was feeling a little sluggish. We're talking about potential energy here. Remember I told you the books on my top shelf have more potential energy than the books on my bottom of my bookshelf. This is the idea that the kid is doing. And then the kid says, hey, by my calculations, standing up here gives me an extra 300 joules of potential energy from gravity. And then the teacher says, but you had to expend energy to get up there. So your total energy hasn't increased. And then the kid says, well, I had Steve lift me up. And thanks for teaching us this stuff, by the way. And the teacher's thinking, oh, great, can't come soon enough. I'm sorry, I just love that kind of stuff. And then my other meme, can easily do vector calculus, cannot balance own checkbook.
Oh goodness.
I'm sorry, I just love this kind of
Life.
stuff. You know, a lot of times, you know, this meme, what I love about this meme is I get Calc 3 students who they start getting really good at Calc 3 stuff. You know, yeah, partial derivatives and, you know, multiple integrals. Yeah, I love this stuff. And they can do all this high level stuff. And then you ask them to do some basic stuff like exponent laws or factor a polynomial, and they'll go, yeah, I don't remember. And I'm like, oh man.
I completely forgot what order of operations were.
What the heck, you know, they forget all their basics, you know, and it's a nightmare. Okay. So are you ready for next steps? So part 2 of today's lecture. What do you mean? Yeah, we're not going to stop. Line integrals. What the heck is it and how do you do it? Well, I don't know. Are you ready for this? What do you mean? We're going to do more integration? Yeah, you're going to learn a brand new integral. I'm done learning new integrals. Please don't teach me anything new. Sorry. They teach you how to do another kind of integral. Yeah, I told you that the rest of this course is integrate, 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 integrate. So let's go over what you know so far, and then we'll do the new stuff. So quick review. Let's go over the integration that you already know how to do, because I like to kind of boost your self-esteem a little bit, let you know we have taught you some stuff that you know how to do here in Calc 3, and then we're going to teach you something new. So what do you know how to do with integration? Well, you know, in Calc 1, they taught you a single integral, you know, you were integrating over a what? You were integrating over an interval, the interval going from A to B. Oops, like that. So, you know, here's your function, da, da, da. And when they were asking you to integrate, you know, you were integrating over this interval here. Okay, fine. Then we did double integrals. Oh, yeah. You're going to take an exam on Monday for me with double integrals. What do you integrate over when you're integrating a double integral? I'll give you a hint. It's not an interval. What is it?
An area?
Close. It starts with an R.
Region?
Region. A region with an area. Yes. So what you're doing when you're doing a double integral is the f might be, some sort of capping surface, z equals fxy, say, and it's hovering over some region here, r, in the xy plane, and you're integrating over the region. Yeah. Then the next step that's also going to be on your exam on Monday, triple integrals. Woohoo! And what do you integrate over when you integrate a triple integral? Your region is this
Volume.
region is 2D. It's a 3D region, which they call what?
Oh, a solid region?
Solid, yeah. So this is 3D. So that's what you know how to do so far. So congratulations. You know how to do all three of those. Single, double, triple. Single integral over an interval. Double integral is over a region in the two-dimensional region, like in the planar region. And yes, you need an area element. And then triple integral, you need a volume element because you're integrating in 3D over a solid. Okay. So what's next? What's next for you is you're going to learn another kind of integral. Oh, man. Don't we know everything already? Well, you're close. We're going to do something called a line integral. You're going to integrate over a line. What? They actually misnamed these. I wish they had named them what they really are. What do you mean? They should be called curve integrals because you're not integrating necessarily over a straight line, although it could be a straight line, but you could be integrating over a curve. Well, wait a minute, isn't that what I did over here in Calc 1? No, you did not. The curve is what was in the integrand, but you were integrating over an interval. So that's not a line integral. Sorry. This is very different. It's another kind of integral. And you study it when you study vector calculus. Okay. So I'm going to do some prep work before we do line integrals because you're not ready yet. One of the big skills that you need when you do a line integral is parameterizing your curve that you're integrating over, because they may parameterize it for you already and just go, oh yeah, here's your parameterization. And then you're like, oh, thank you, God. But they might be mean and they may go, here's a line integral and here's kind of what the curve is about. And you got to go parameterize it. And you probably forgot how to parameterize because we did it way back when we studied vector valued functions. That's right. And I taught you the quick tricks on how to parameterize, but there's a little bit more to it. So we're going to look at parameterization of something kind of fun. Check out this this curve, which is actually piecewise smooth. So when you do line integrals, you do need your curves to be piecewise smooth. Smooth means it doesn't have any sharp corners. Well, this curve here, which it goes, there's like sharp corners in there. Yeah, but you can cut it into pieces where each piece is smooth and doesn't have a sharp curve. So we're going to actually parameterize each of those pieces. Yeah. So we're going to look at an example that involves parameterization. Then we'll look at line integrals. Okay. So remember, a curve is smooth if you've got your R of t, your vector value function representing a curve, and the derivative is not the zero vector, because the minute you've got a zero vector for your derivative, that's where you've got a sharp corner or a cusp or something. All right, so let's parameterize. I'm going to show you two different ways to parameterize this piecewise curve. Okay, I'm going to show you my way, which is the easiest way, and then I'll show you the way a book does it, which I think is harder. But it's good to know that parameterization is not unique. And we learned that way back in like the first month of this class, that when you would parameterize or give me the parametric equations for a line, I had to be very careful because your answer might be legitimate and my answer looks different from yours, but it's just as legitimate because parameterizing is not unique, but it does have to match. You can't just come up with anything. I have students that, try to argue, well, you said parameterization isn't unique and mine's different from yours. And I'll go like, Yeah, but yours doesn't represent the same curve that we're doing. You can't just like pull stuff out of the air and put it together and go, well, there you go. That doesn't work. Okay. So notice that the first leg of the journey of this curve is, we'll call it C1, and I'll do this in colors here. So C1 we'll do in blue, and then the second leg of the journey is C2 going that way, and then the third leg of the journey is going straight up. There's C3, okay? So we're going to have 3 parameterizations for each piece of this curve. So C1. Okay, notice that C1 is in the XY plane. What does that mean? It means that Z is equal to 0, or it means the third component is zeroed out. So when we try to get a vector valued function, and also we need the time range, these are all the things that you have to tell me when you're parameterizing. Everywhere I'm putting question marks. No guessing. Okay, so the good news is the third component is going to be 0, because that curve 1 is just flat in the XY plane. Now, but what about the X and Y though? What the heck am I going to put there? Oh dear. Well, look at the curve. Notice it starts at 0, 0, 0, fine. And it's moving along the Y-axis, which means X stays 0 the entire journey. So I can put a 0 there for the X component. But then Y is changing between 0 and 2. So Y is variable. That means you need to put a variable here in that middle component. Well, what variable should I use? I'm confused. Well, shoot, just pick one. T, and T is typically the parameter that we use when we're parameterizing. So we're going to say it's T, and T varies. And this is where you can pick your interval for time. So in order to make this curve match over there, and since Y went from 0 to 2, our time will go from 0 seconds to 2 seconds. And boom, we just parameterized the first curve. And I'm done with C1. Let's parameterize the second leg of our journey, C2. C2 is also flat in the XY plane. Good news. That means his third component is also going to be zeroed out. So we'll call this vector valued function R2 of t. And we will also have to figure out what the range of t is for that vector value function. So the third component is again zeroed out because we're flat in the XY plane. Okay. Then what? Oh, right. Let's look at where the starting and stopping on this straight line. All right. X is changing from 0 to 1. So X has to be variable. Y, good news. Y is staying at a 2 the whole time. Never changes. It's constant. So there you go. Put a 2 for the Y component. Constant. It's a 2 the whole time. So who's variable? X. So we'll put a T there. And then since X is starting at 0 and ending at 1, how about we'll just have the time T start and end at 1. So that way this parameterization matches this straight line exactly. Yay! And last but not least, let's do the third curve. It's where you strap on a jetpack and whoosh, take off from Earth, baby. C3, shooting straight up. So I hope you can see that the Z is not going to be 0 now. Oh, no. So we'll call this R3 of t. We need to fill in these blanks. And we also need to figure out the range for t for that vector value function to match that curve or that piece of the curve. So what are we looking at here? If I look at the starting and stopping, it starts at 1, 2, 0 and ends at 1, 2, 1. Hey, good news. The X and Y are both constant. X stays a 1 and Y stays a 2 the whole way. Nice. So who's the variable guy? Z. Oh, so let him be the T. And since he starts and stops at 0 and 1 respectively, we'll just have T starting and stopping at 0 and 1 seconds respectively. And we're done parameterizing the entire curve. We needed 3 separate parameterizations. That's not a problem. We can do it. Okay, questions?
How did you do for X again?
Which one? The first, second, or third curve?
First one, C1.
The first one, do you notice C1, the starting and stopping points for the X coordinate is 0 the whole way?
Right.
So that means he gets to be a 0.
Is there, but oh, because that's T1. Oh, because the T's in the Y coordinates. That makes sense now.
Yeah, it was the Y that was variable for that leg of the journey.
Okay. Yeah, that makes sense.
Now, I'm going to show you an alternate parameterization. You're not going to like it, but I want you to know that the book that I got this from, Larson, they gave this as their answer. I like mine better. So I just want to show you how Larson did it, okay? So for C1, the Larson did it this way, okay? They called it R1. So here's another alternate parameterization. Remember, parameterizations are not unique. What if they said, okay, well, yes, the X and Z are 0, so that did match my answer, but they decided to use twice T for the Y component, where their time, instead of going from 0 to 2 seconds, it goes from 0 to 1 second. Now, why is that working? Well, if you plug in 0 seconds, it does start at 0, 0, 0. And if you plug in the 1 second, you do stop or end at the ending point, 0, 2, 0. Well, which way is better, yours or theirs? It doesn't matter. You know, parameterization isn't unique just so long as it matches the curve. Now, this is what they did for C2. They did call it R2. And they did notice that the Z is zeroed out the whole time because you're in the XY plane. And since the Y coordinate stayed 2 the whole time, Y is constant. And then this part you're not going to like, because what they put for the X is T minus 1. What? This is how come. They wanted their clock, you know, where the time here, the clock starts at 0 seconds and ended at 1 second from the previous curve. They want their time to start where the previous clock left off. Okay, so if we have time starting at 1 second, then that means that your variable components have to be a little bit different look. So if you plug in 1 second in a T minus 1, 1 minus 1, it does look like you're matching the starting point for C2. Okay, but then what's the ending point? Well, you need the X to end at 1. So what should we finish the time clock here in order to have the X coordinate end at 1, knowing that X is T minus 1? Well, when does T minus 1 equal 1? Solve that for T. What do you get?
2.
So we'll have the clock end at 2 seconds. And then that is a fair parameterization of the second leg of the journey, where the clock begins where the clock left off from the previous curve. And then finally, this text had their C3. They want their clock to start where the last clock ended. So we need our clock to begin at 2 seconds. And the X and Y coordinates, when we're shooting straight up here, stay constant at 1 and 2. And then the Z is what's changing. So they had their Z be T minus 2. Notice when you plug in the starting time of 2 seconds, your Z does begin at 0, so that works. And then if you have your T stop at 3 seconds, your Z will indeed stop at 1, and so it works. So this is an alternate way to parameterize the curve. It's not my favorite way. Don't you like my way better? So what I want to let you know is that I give you permission to do it my way. Why is my way better? Because it's easier to just reset your clock back to 0, chink, every time your curve does its thing. I like to do it that way. You don't have to. Well, will it make a difference for the future? No. So pick the less painful way to parameterize, because we're going to be doing quite a bit of parameterization in the next couple weeks. And so you want to, if you like to avoid pain, I mean, I do. I like to just reset my clock to 0 for piecewise smooth curves. And so go for that, so you don't have to do the painful way of keeping your clock ticking. Okay. So what? Now let's look at the first type of line integral, and hopefully I'll do a quick penumbra of a proof, and then we'll do one example, and then I'll set you free, and then we'll start this up again next week. Okay. So there's going to be 3 kinds of line integrals that I want you to be familiar with in my class, and you're going to have one of each on exam 4, and you'll have one of each on the final. Telling you in advance what's going to be on there, so know how to do it. So what is the first type? Well, the first type is called a scalar line integral, because it doesn't have anything to do with vector fields. And the best application of a scalar line integral is mass of a wire. So if you've got a wire right here, here's a wire, it's a curve, and you cut it up into intervals, you know, we're doing that whole partition thing. And you look at the ith subarc, you know, hey, there's a subarc. And the arc length of that ith subarc is delta s sub I. Remember little s was arc length back when we did arc length? I know you forgot. It's okay. If you pick an arbitrary point, x sub I, y sub I, z sub I in each subarc, and if the length of each subarc is super small, you can approximate the entire mass of your wire by taking the mass or the density function on that wire and multiplying it by a little piece of arc length, and then adding up all n subintervals, subarcs. And then of course you're going to let the norm of the partition go to 0 and cut up in teenier and tinier little pieces. So you let the longest subarc approach 0, take the limit, and you get a line integral. So there's 2 line integrals I want you to know about, the 2D version and the 3D version. So for both of them, though, you are taking the limit as the norm of a partition goes to 0 of a Riemann sum. So there's the 2D Riemann sum. So this set gets equal to a line integral. And you put a C down here, which tells you it's a line integral, not the kind of integral that you did in Calculus 1. Okay. And for the Riemann sum that you have in a 3D, so you'd have a 3D, like that picture up there, that's a 3D wire. You would have some density function, fx sub I, y sub I, z sub I, and a little subarc arc length. Take the limit as the partition goes to 0, and your 3D arc, or your 3D line integral looks like that. Now, this is the definition of a line integral, and you have some fancy notation here. And you notice here, this says ds, not dx. That says ds. Please note, and yes, it makes a difference, ds, because that's what's called an arc length element. This ds here is going to be an arc length element. So let me remind you, when we did arc length back like 2 months ago, arc length s was the integral of speed. Do you remember this? You probably forgot.
No, I do remember that.
But if you remember it, it's going to help you in this chapter big time. Because the arc length element for a 2-dimensional curve, you're just going to take the magnitude of the velocity vector. You did this a couple times for me. And that's going to help you get your arc length element times dt. This is your ds right there. So how do you evaluate one of these weird line integrals? Well, you got to turn it into a regular integral. Well, how do I turn it into a regular integral? I'm going to show you. So let's do the 2D version first. Here's a weird line integral. You got like the density function, and then you got this arc length element. To turn it into a regular integral, you have to know the interval that you're integrating on. And then when I say interval, what the time range is. Time going from a seconds to b seconds. The density function, everywhere you see an x, you're going to substitute in its place the x component from your vector valued function. So you have to have your curve parameterized for you. If the curve is not parameterized with the vector valued function, you got to do that work and figure out the range of time also, like we did on that preparatory example. Now, if they give it to you already, you're like, hey, then half the work's done for you. And then you substitute the y of t in place of any y's that you see in your density function. And then the arc length element, and this is important, is going to involve that nasty square root with the sum of the squares of the components of your derivative function, your velocity vector, essentially. And that's what, and then you can integrate that if it's integrable. Good luck. Because sometimes having that nasty radical in there might make it not integrable, and you'll have to whip out your graphing calculator to do it. Now, what about the 3D version? Because you'll have 3D line integrals as well. So let's say you're looking at this 3D generic line integral. How do you turn that into a regular integral that you can do business with? Well, again, hopefully somebody already parameterized your 3D curve using a vector valued function, r of t, and you've got time ranging from a to b seconds. So the range of time goes for your limits on your integral. F, the x, y, and z, again, you have to substitute. Anywhere you see x's, you put the x, substitute the x component of your vector valued function. Anywhere you see the letter y, replace it with whatever the y component is of your vector valued function, and z's get replaced with z of t. And then you've got that horrible radical, which is your arc length element. Magnitude of the velocity vector. And then you integrate with respect to time t. And that's it. I'm going to do one example, and then we'll call it a day. And we'll pick this up next time. I know you're probably not going to look at this stuff until after your exam, but I want you to at least have, once your exam is through, you know, get busy doing your homework, because, you know, this class doesn't end till the final. Keep it going. Don't run out of gas. Some of you, I think, are running out of gas. You know who you are. Don't do that. It's too early. You're running a marathon. You only have a couple miles left. Don't give up. Keep going. So I want you to notice good news for this easy peasy example. Here's a line integral. Okay, how do I know it's a line integral? Well, it's got that look, you know, it's got the letter C down underneath the integral symbol. It's got ds. That stands for arc length element. And it's weird. You know, I got x's and s's. Yuck. And then the good news is they already parameterized the curve for you, and they gave you the range of t. Beautiful. What does that mean? That means this line integral can easily be converted into a regular single integral that you can actually evaluate. Ha-ha. So you follow what the previous page said to go do right here in this theorem. If you don't, then prepare for pain. So let's get this arc length element done. Let me get r prime here real quick, because I'm going to need it. So you know the drill. How do you take the derivative of a vector valued function? Shoot, we did that a couple months ago. Derivative of each component, 1, and then we have 4/3 times 3/2 t to the 3/2 take away 1, I believe is a half, times, and then comma, and then the derivative of 1/2 t squared, I think is t. If I clean this up a little bit and reduce to lowest terms, I'm going to get 1. These 3's cancel, 2t to the half t. Okay. So the arc length element, the magnitude of this velocity vector is the square root of the sum of the squares of the components, right? Like so. And if I clean this up a little bit, I'm going to get 1 plus 4t plus t squared. Okay, so that's that. So over here, they're giving me the time, 0 to 2. This density function, no. You're going to replace x with what? The x component that you steal off of the vector valued function. In this case, it's just t, but it could have been something worse. So t plus 2. And then this arc length element, the square root of 1 plus 4t plus t squared dt. Now, is this even integrable? This is a hot mess, and it looks like it wouldn't be. But the good news is this one is. And you're going to use the power rule with u sub. And as usual, I like you to tell me the u and the du. So if you let u be everything under the radical, let me rewrite it in descending powers of the variable just to make it nice. T squared plus 4t plus 1. What's the derivative of that? Well, that doesn't look good. Well, the good news is if you factor out a 2 from this du, you do have t plus 2 and the dt already in the integral. What's the only thing that's missing that you need? A 2. Well, that's good news because that's just a constant multiple that we can put in there provided we divide out. Ah, nice. So then what? Well, the intermediate step would look like this is 1/2 times the integral of square root of u, which is the integral of u to the half. And that's going to be 1/2 times 2/3 u to the 3/2. And I'll reduce and back substitute. And then evaluate this antiderivative between the limits of 0 and 2. It's not going to be a very nice number, I'll be honest. It's going to be pretty gross, okay? You know, that's all I can say. 2 squared plus 4 times 2 plus 1, yuck, to the 3/2. And then when I plug in a 0, well, that's not too bad. And this is going to be like 13, so you're going to get 1/3 times 13 to the 3/2 minus 1. I'm just going to leave it. That's the exact answer. The approximate answer, if you punch this up in a calculator, it's about 15.29. And typically when you do one of these scalar line integrals, you should get a positive result because they typically represent mass of a wire, and you don't want to get negative mass. So usually these scalar line integrals will be positive results. Now, other line integrals we're going to do in the future, when we do next time, when we do more line integrals involving vector fields, you could get positive, negative, or 0 because it's going to represent something else. It's not going to represent a mass of a wire. Okay, so that's all I got today. So congratulations. I hope you have a great Friday. And so